The liquid battery that powers your life has reached its physical limit. To go further, we have to turn chemistry into solid stone. Since the early 90s, the world has been running on a specific type of magic that is not magic at all, but a very precise trade-off of chemistry. We call it the lithium-ion battery. It is in your pocket, your ears, your laptop, and increasingly in the floorboards of your car. For 3 decades, engineers have squeezed every possible drop of performance out of this liquid-based architecture. We have optimized the anodes, refined the cathodes, and thinned out the separators, but we have reached a ceiling. A physical, non-negotiable boundary dictated by the laws of thermodynamics and material science. The liquid electrolyte, the very medium that allows energy to flow, has become our greatest bottleneck. It is volatile, it is heavy, and it is standing in the way of a true energy revolution. To break through, we are moving away from the fluid and into the solid. This is the race for the solid-state battery, a shift in engineering that promises to triple energy density, eliminate fire risks, and redefine how we move across the planet.
To understand why we need to change everything, we first have to understand the fundamental compromise of the modern battery. Every lithium-ion cell you use today operates on a relatively simple principle. You have 2 electrodes, an anode and a cathode, kept apart by a thin plastic separator. The space between them is flooded with a liquid electrolyte, usually a mixture of lithium salts and an organic solvent. When you charge your phone, lithium ions move from the cathode through the liquid and nestle into the anode. When you use your phone, they swim back. The liquid is excellent at its job because it provides a perfect contact surface. It wets every microscopic nook and cranny of the electrodes, allowing ions to flow freely. However, this liquid is also our greatest liability. These organic solvents are highly flammable. If a battery is punctured or if it overheats due to a short circuit, the liquid electrolyte doesn't just fail, it becomes the fuel for a catastrophic fire. This is known as thermal runaway. To prevent this, modern electric vehicles require massive, heavy, and complex cooling systems and reinforced steel casings. We are spending a huge portion of our weight and volume budget just to keep the liquid chemistry from exploding.
Beyond safety, the liquid electrolyte imposes a strict limit on energy density. In a standard battery, the anode is typically made of graphite. We use graphite because it is stable, but it is bulky. The holy grail of battery engineering has always been the lithium metal anode. Using pure lithium metal instead of graphite would allow us to store significantly more ions in a much smaller space. But there is a problem. When you try to use lithium metal with a liquid electrolyte, the battery essentially commits suicide. During the charging process, the lithium ions do not always deposit in a smooth, flat layer. Instead, they form microscopic needle-like structures called dendrites. These dendrites grow through the liquid, eventually piercing the plastic separator and touching the cathode. The moment that happens, you have a hard short circuit, a massive release of energy, and usually a fire. For decades, the dendrite problem has kept lithium metal anodes in the lab and out of our cars. The liquid is simply too soft to stop them. This is where we transition from the liquid limit to the solid frontier. The core idea of a solid-state battery is to replace the flammable liquid electrolyte and the plastic separator with a single, solid piece of material. This material must do 2 contradictory things at once. It must be an electrical insulator, meaning it stops electrons from passing through it, but it must be an ionic conductor, meaning it allows lithium ions to zip through its crystal lattice as if it were a liquid. This is an immense engineering challenge. We are essentially trying to build a stone that acts like a highway for atoms. In the world of material science, we have identified 2 main candidates for this role: polymers and ceramics. While polymers are easier to manufacture, ceramics are the true heavyweights of the solid-state world. Specifically, materials like LLZO, a complex ceramic made of lithium, lanthanum, and zirconium oxide, or sulfide-based solids.
A ceramic separator is a game changer for one primary reason: mechanical strength. Unlike the flimsy plastic used today, a dense ceramic layer can act as a physical barrier that dendrites cannot easily penetrate. It is like replacing a chain link fence with a reinforced concrete wall. Because we can finally stop dendrites, we can finally use the lithium metal anode. This is the triple threat of solid-state engineering. By using lithium metal, we dramatically increase energy density. By using a solid ceramic, we eliminate the flammable liquid, making the battery inherently safe. And because the system is safer and more energy dense, we can remove the heavy cooling and protective structures, further increasing the efficiency of the overall vehicle. We are moving from a world of chemical management to a world of structural integrity.
The transition to solid state is not just a change in materials, it is a total reimagining of battery architecture. In a traditional liquid cell, the components are rolled up like a jelly roll or stacked in a pouch. But working with ceramics is different. Ceramics are brittle. They do not like to be bent or squeezed unevenly. This brings us to the biggest hurdle in the race, the interface. In a liquid battery, the electrolyte flows into every gap. In a solid-state battery, you have two solid surfaces pressed against each other. At a microscopic level, these surfaces are rough. If the contact isn't perfect, the ions can't jump from the electrode into the electrolyte. They get stuck. To solve this, engineers have to apply massive amounts of pressure to the battery stack or develop soft, solid electrolytes that can deform slightly to maintain contact. This is the current front line of material science. Companies are experimenting with hybrid systems, perhaps using a tiny amount of liquid or gel at the interface to ensure ion flow while keeping the bulk of the system solid. Let's look at the numbers, because the math of energy storage is what drives the investment of billions of dollars. Current high-end lithium-ion cells have an energy density of around 250 to 300 watt-hours per kilogram. To get a standard electric SUV to travel 500 miles on a single charge, you need a massive battery pack weighing over half a ton. Solid-state technology aims to push that density past 500 watt-hours per kilogram. In practical terms, this means you can either have a car with the same range but half the battery weight, or keep the weight and double or triple the range. Imagine an electric vehicle that can travel from New York to Chicago without stopping, and then recharge in less than 10 minutes. Because solid-state electrolytes can handle higher temperatures and higher voltages, we can pump energy into them much faster without the risk of the liquid boiling or catching fire. We are looking at a future where charging an EV is no longer an event you plan your day around, but a brief pause no different from filling a tank of gas. As of 2026, the race has moved from the laboratory to the pilot production line. We are seeing a divergence in strategies among the global giants. Companies like QuantumScape have focused on a proprietary ceramic separator that they claim can eliminate the dendrite issue entirely. Their data suggests their cells can retain over 80% of their capacity even after 800 cycles, which is the gold standard for automotive longevity. Meanwhile, Toyota, a longtime advocate for solid-state, has pivoted its massive manufacturing might towards sulfide-based electrolytes. Sulfides are interesting because they are slightly softer than oxides, making it easier to maintain that crucial contact between the layers. Toyota's goal is to bring a solid-state vehicle to market that offers a 1,200-kilometer range and a 10-minute charge time. They aren't just looking to build a better battery, they are looking to make the internal combustion engine obsolete overnight. But if the science is so settled, why isn't every car on the road today using this? The answer lies in the brutal reality of gigascale manufacturing. Our entire global supply chain is optimized for liquid lithium-ion. We have spent hundreds of billions of dollars building factories that coat wet slurries onto metal foils. Solid state requires a completely different process. You're dealing with ceramic sintering, vacuum deposition, and ultra-dry rooms, because many of these solid electrolytes are sensitive to even a trace of moisture in the air. If a sulfide electrolyte touches humid air, it can release hydrogen sulfide gas, which is toxic. So the engineering challenge isn't just, can we make one battery? It's, can we make 1 million batteries per year at a price the average consumer can afford? Currently, solid-state cells are significantly more expensive to produce than their liquid counterparts. The race is now a cost reduction race. There is also the issue of volume expansion. When lithium ions enter an anode, the anode physically grows. In a liquid battery, the liquid just moved out of the way. In a solid battery, that expansion creates immense internal stress. If the ceramic separator is too rigid, it will crack. If it cracks, the battery fails. Engineers are now designing breathing battery packs that use sophisticated spring systems to maintain constant pressure on the cells as they expand and contract during charge cycles. It is a masterpiece of mechanical engineering hidden inside a chemical storage device. We are no longer just chemists. We are structural architects working at the nanometer scale. The implications of winning this race extend far beyond the driveway. The liquid limit has been the primary barrier for electric aviation.
To get a commercial airliner off the ground with electricity, you need power-to-weight ratios that liquid batteries simply cannot provide. Solid-state technology changes that equation. With 500 or 600 watt-hours per kilogram, short-haul electric flights become not just possible, but economically inevitable. We are also looking at a revolution in grid storage. Imagine massive, solid-state battery banks that are completely fireproof, sitting in the basements of skyscrapers or in the middle of dense cities, buffering renewable energy from the sun and wind. The safety profile of solid-state allows us to put high-density energy storage in places where liquid lithium-ion would be a liability.
As we look toward the end of this decade, the not magic reality is that the transition will be gradual. We will likely see solid-state batteries debut in premium, high-performance vehicles first, where the cost can be absorbed by the high sticker price. From there, as manufacturing yields improve and the ceramic bottleneck is solved, the technology will trickle down to mass-market cars, power tools, and eventually the smartphone in your pocket. We are witnessing the final days of the liquid battery era. It has served us well, taking us from the first portable camcorders to the verge of a global EV transition. But to go the rest of the way, to truly decarbonize our transport and our lives, we have to leave the liquid behind.
The material science is clear. The engineering path is mapped out. The capital is flowing. We are turning chemistry into stone because stone is more stable, more powerful, and more resilient. The race for the solid state is not about a sudden breakthrough or a lone genius in a garage. It is about thousands of engineers solving the interface problem, the pressure problem, and the scale problem. It is about moving past the liquid limit and into a future where energy storage is as solid and reliable as the ground beneath our feet. This is the next chapter of the electrical age, and it is being written in the lattice structures of advanced ceramics. The miracle isn't that we found a new way to store energy. The miracle is that we are learning how to build it, one atom at a time at the scale of millions. When we look back at this period in history, the shift to solid state will be seen as the moment electric mobility became the default rather than the alternative. We are removing the final buts from the conversation. Solid-state engineering is the systematic deletion of those excuses. It is the final brick in the wall of the fossil fuel era. The race is on, the players are set, and the finish line is a world where energy is denser, safer, and more accessible than ever before. It's not magic, it's the inevitable result of pushing material science to its absolute edge.